Our next speaker is Andrea, who is going to give a 12-minute talk. Then we'll have Lucas, and we'll have some time for questions about the flash talks. So, Andrea, you have 12 minutes, and I will give you a 5-minute notice before the end.
Hello, everybody. I'm very excited. This is obviously my first talk. I'm a master's degree student, and I collaborated this summer with Fermilab. And we worked on graph neural networks for constraining cosmological parameters and performing domain adaptation for switching in simulation while training and testing. So the task at hand is inferring cosmology from simulations. And this project is, let's say, based on the belief that modern machine learning approaches, such as neural networks and so, have the ability to extract richer, nonlinear information from complex datasets with respect to summary statistics. The dataset we're working on is the CAMELS dataset. I see my GIF is not working, but doesn't matter. And what we're building on is a paper from Pablo Villanueva-Domingo and Francisco Villascusa Navarro from this year, which introduces the architecture CosmoGraphNet, which is a graph neural network for treating galaxy catalogs from the CAMELS dataset as they should be treated, so as graphs. The novelty in this is the fact that with a graph neural network, you can get these galaxy catalogs and actually encode them with all of their information. So you don't just get the galaxy clusterings and construct a table with galaxy 1 features, galaxy 2 features, galaxy 3 features, and then throw it into a machine learning model and hope that it does predictions which are intelligent. What you'll do is actually give it a graph to the graph neural network, and that will have some particular structure that will encode the topology and the edges. So how these graphs are constructed is basically you will calculate the centroid of the graphs, and then you will calculate relative positions and angles and encode these informations for the edges of the nodes, and then feed this to a graph neural network. And once you feed this to the graph neural network, this will generate a vector of encoding that represents the graph. And on that vector, you will put on a multilayer perceptron, which is a regressor, and will predict the mean and standard deviation of the parameter we're trying to infer, in this case, omega m. So this is all great work that I didn't do. It's done by the authors I mentioned before. Where does the interest of my project lie? The interest of my project lies in this struggle for domain generalization. So when the authors tried training in Illustris and testing in Illustris, everything was fine. When they tried doing the same for Simba, everything was fine. When they tried switching simulation, everything crumbled. What happened? What happened was that probably the model just learned artifacts, just learned the simulation. So there wasn't actually any physics being learned. And so CAMELS datasets are very prone to this kind of analysis that we are doing because they are developed with different subgrid physics, different numerical resolution, Gizmo code or REPO code for different suites. And so what you'll obtain is if the model is actually learning the numerical stuff, you will notice when you'll go to another simulation. So this is a good framework into which evaluate some domain adaptation techniques. Again, the GIF is not working. What you should see from z equals 9 to redshift 0, the evolution of different simulations where you would see that the gas temperature, but we have seen it many times in this conference at this point, so I think you know the image where you would see Illustris, which is still pretty blue, and Simba just blows up because it has extremely different numerical values from which the model should work on, which obviously, if you perform no domain adaptation, means it will give very different numbers when doing prediction on the other set. Okay, so domain adaptation. What is domain adaptation? Domain adaptation is basically a technique to improve the performance of a model in a target domain. So let's say we have a target domain of which we have very few labeled data. You have only unlabeled data. And what you can do is use that data in an unsupervised fashion. Clearly, what is the objective here? Doing this with real data. So one day, using real data as unlabeled data, of which we obviously do not have the parameter, or else we wouldn't be doing all of this. And use it to train domain mixing with the actual simulation, and then use regression with that domain adaptation technique. There are different domain adaptation techniques. There are distance-based methods, adversarial methods, more obscure methods that I have not studied. And what we're focused on today is distance-based methods for what we have done, and adversarial methods for what could be future work on this. Distance-based method. We use maximum mean discrepancy. So you remember in the CosmoGraphNet architecture, you go from a graph, construct the graph neural network, get to the vector of encoding. So what you'll do on the vector of encoding is basically you will get from two simulations, simulation A and simulation B, for example, Simba and Illustrious in our case, and get the two vector encodings, or in actual practical cases, the batches of vector encodings, and calculate the maximum mean discrepancy between these two batches of samples. Which means that you're basically evaluating how similarly the values are being encoded. So in this very not funny example, but it's funny to me, we have two domains, dogs and fishes. Dogs and fishes, a dog will obviously be encoded more similarly to a dog than to a fish, or else your encoder has clearly a problem. But when you go to domain mixing, so you want to maximize the similarity between off-diagonal stuff. So dogs and fishes, fishes and dogs. So in the numerical function, you can see the last term. If you try to minimize this MMD squared distance, you will see the -2 divided by n with the sum of the kernels between different domains. You want to possibly maximize that term, or minimize it with the minus sign, to have good domain mixing and obtain dogs and fishes. So what is the architecture? The architecture is, as we explained, two data loaders. This is what we have done. Two data loaders going and creating these two vector representation, calculating the loss on the MMD, calculating then the loss on the regressor for just the domain A, for which we have the labels. And at that point, back propagate through all of this and hope that it learns a much more solid encoding. Now, this is the figure I would like for all of you to understand, which if you understand what happens here, you basically have understood everything we are doing. Basically, this is an isomap. So it's a 2D low-dimensional representation of the encodings of the GNN, so the vectors, how they are encoded in the latent space, represented in 2 dimensions. As you can see on the left, without MMD or any domain adaptation, on the right with MMD and domain adaptation. On the left, you can see that there are two very distinct distributions. One is the Simba, and one is the Illustrious, and how they are being encoded in the latent space. This is clearly not desirable because there is no domain mixing happening. Okay, imagine that you are a regressor working on that encoding. You can't use the same regressor for those two encodings because obviously they're encoded in a very different way. What you want, looking at this graph, is a clear color gradient, which means that the position in the latent space is related to the actual label of the data point, and also that triangles and circles are very well mixed, so that you can use one single regressor for both. In that case, you would have obtained a good, let's say, domain mixing and embedding of useful information for your regressor to work on. So we can see, as a result, that we obtain a much better cross-simulation result on the relative error on the chi-square. So we're predicting both the mean and the errors better. Disclaimer, it is still much worse than on same simulation, so there is a lot of work to be done, but this is a proof of concept paper, not a final result paper. This is the same on the other simulation. It is less evident in the latent space, but it is still clear that there are two very distinct distributions between triangles and circles. And these are the results. Again, here there is like 1/3 of the relative error to compare to the CosmoGraphNet paper from the two authors mentioned before. So there are many limitations. Limitations that first of all, this could be made with more flexible approaches than MMD, so using adversarial-based approaches. And this is like my side of the stuff because I'm a computer science guy. I'm not very much an astrophysical guy. These are other members of the team. But also, for what regards the astrophysical stuff, is that there is a lot of physical bias to be put on the GNN. As the first person who talked at this conference said, you can't expect to put a GNN over galaxy catalogs and just encode everything of the galaxy catalog. You should be able to put some bias inside the GNN. There are techniques to do this, and insert bias in the GNN towards encoding the information that you're interested in. Moreover, we could use more simulations, both for training and for testing and for having more reliable, let's say, results. As for the adversarial methods, I just provocatively, as I've finished my time, put out two strategies that could be used and that are actually pretty much already implemented, but I have not managed to work them because they're very hard to train and very sensible. One is domain adversarial neural networks, which use a gradient reversal technique for the domain mixing. So there is an adversary trying to guess the domain labels, and you will revert that gradient in such a way that the encoder learns the opposite of that objective function. So it's a min-max problem where the encoder and the classifier share the gradients just in an opposite sign to try and achieve the different objectives. And the other is basically the Frankenstein of domain adaptation, in which you first do a pre-training where you train encoder and classifier from the source. You keep the classifier. Then you train a target encoder. It doesn't have to be a CNN in the paper. It simply was a CNN. You train the target encoder to mix it with the source encoder through a discriminator. Then you attach this target encoder and the classifier. And using this Frankenstein, you actually obtain results which are better than with the previous method. So this is everything. Thank you very much for your attention.
Thanks a lot, Andrea, for the great talk. Any question for Andrea in the audience? There is one there.
Very nice talk, thank you. So I'm curious, in real life, how would you do this? Because you only have one universe.
Exactly.
Have you thought about this?
So this is one of the most obvious problems, and you're correct. What one could think to do is, because actually these are very small volumes of the universe, is to break up our universe into small voxels and train to use those as the unlabeled data set. The problem there would be that there would be only one value of omega m. So how do you figure out the fact that it's true, you're encoding in an unsupervised fashion both of the samples from the two worlds, the real data and the simulation. But in one case, you have a distribution of omega m. In another one, you have only one value of the omega m, which is the true one. So I don't have an answer for that. But the main idea would try to break up the universe into voxels, to small boxes, and resolve the problem of not having a distribution for omega m.
Thank you. That makes a lot of sense.
Any question on Zoom? Yes, there is one.
So Nathalie DeSanti is asking, which galaxy properties are you using?
Which
galaxy properties are you using?
There are also on the slides, and from the galaxy catalogs, we're getting the maximum circular velocity, stellar mass, and stellar radius, and obviously the positions. And here is another provocative thing for future work. One would want to ultimately work both on simulations in an domain-independent way and on simulations only on things that you could actually have on real data. So I'm a computer science guy, but I don't think you have all of these actually when you go to analyze real data. You don't have all of the information that we use. So the ideal net would use, in a domain-invariant way, the galaxy catalogs with only positions and be able to give some good constraints. At the moment, this does not happen. Like, we are very distant from having this kind of results, but like that would be the ultimate objective, like training something with domain adaptation techniques that is able to get the galaxy catalogs, construct them as graphs, and use those topological encodings and just a few features that are actually observable in the real universe to train, so that when you go to the realm of real data, you both have the domain-invariant encoding and all of the data that is necessary to actually do the inference.
Thanks. Maybe one last question from New York, if any.
Any questions? Karthik? Thanks for the wonderful talk. So you showed that the performance of training on elasticity and applying to Simba or the other way around improves dramatically after doing the domain adaptation. But the process of domain adaptation itself essentially throws away some information in trying to get the two data sets to align. Like, it's finding this domain invariant representation. If you take that domain invariant representation and do the train on elasticity and apply to elasticity with just that reduced representation, what do you find for the accuracy?
I didn't hear the last part of the question, sorry.
No worries. So essentially, like, instead of using all the information in a single simulation, if you only take the domain invariant information in a single simulation and train a regressor, what kind of accuracy do you find?
It's not an analysis that we did, honestly. So I wouldn't know how to respond to that.
Okay, thank you.
The only thing that we observed is actually the increase in, okay, we split into a part that we do not analyze of the unlabeled data and see how much. So, like, the unlabeled data on which we test to assess the robustness cross-domain is not even used for the encoding. So at the moment, even though at the application on real data, you wouldn't do this because you would want to use all of the data that you have, to assess the robustness more reliably, there is a split in training and validation and testing also in the unlabeled data. So the increase in performance in the other set should be pretty validated by the numbers that we achieve. I don't know if this is answering your question. I feel like I don't know if I really answered that. If I haven't, please let's talk later. I don't want to rob time from everyone.
Will do. Thank you.
Thanks again, Andrea.
Thank you very much for the question.
Yeah. Oh, no, I don't. We won't take any more questions, but I really encourage you to put them on Slack. I'm sure there are lots of other questions. So thanks again, Andrea. And our next and last speaker is Lucas.